We're surrounded by data. It's everywhere. But have you ever stopped to think about how we get from this just chaotic mess of information to the super reliable, orderly systems we use every single day? Well, in this explainer, we're going to pull back the curtain and uncover the core ideas that bring control to all that chaos. Let's dive in.
I mean, seriously, think about it for a second. You can zap money to a friend in an instant, and you just trust that it'll get there. There's no stress. But why? What's the secret sauce behind that rock-solid confidence? Today we're going to look at the magic that makes it all work. And it all starts with a problem that's as old as information itself. See, before the slick, organized systems we have today, managing data was pretty much a free-for-all. I want you to picture a world with no central source of truth, where every little piece of information was stuck in its own separate bubble. It was, to put it mildly, a recipe for total chaos.
Let's just take a college, right? The accounts department, they've got their own files for student fees. The library has a completely separate system for who has what book. And the exam department? Yep, you guessed it, another totally different file just for grades. Each one is its own little island, and when you have all these islands of data, you get some major problems.
And this slide really lays it all out. On the left, you've got that old file system approach. Let's say a student changes their address. You'd have to go and manually update that info in the accounts file, the library file, and the exam file. If you miss just one, boom, you have conflicting information. It's a total nightmare of duplicated, inconsistent data. And what if the power goes out while you're saving a file? Poof, your data could be gone or corrupted. It was obvious this whole system was just broken. So, out of all that chaos, a hero finally emerges, the Database Management System, or as we all know it, the DBMS. This was the game-changing idea that was finally going to bring some serious order to the world of data.
So what is a DBMS, really? Honestly, the best way to think about it is like a super smart, highly organized librarian for all your data. It's a piece of software that sits between you and the actual data. You don't have to worry about the messy, low-level details of where and how everything is stored. You just tell the librarian what you need and it goes and gets it for you, making sure all the library's rules are followed every step of the way.
And the benefits of doing it this way are just massive. You know that data duplication problem we were just talking about? Gone. Sharing information between departments being a pain? Solved. And things like security and backups? The DBMS handles all of that automatically. It was a complete game changer.
Okay, so we've got this amazing tool to manage our data. But where do we even begin? You can't just dump a bunch of random information into a DBMS and hope for the best. You need a plan. You need a blueprint. And in the database world, that blueprint is called the Entity Relationship Model, or the ER model. It's how we design the entire structure of our data before we write a single line of code.
You know, at its core, it's actually pretty simple. An entity is just a real-world thing we care about, like a student. An attribute is a property or a detail about that entity, like the student's name or their roll number. And a relationship is just how these different entities connect to each other. For example, a student enrolls in a course. Simple as that.
And here you can see that idea in action. On the left, that's the blueprint, right? The technical definition from the notes saying a student has a roll no, a name, and marks. Then, on the right, you see that blueprint come to life as a simple, clean table with actual student data in it. It's a perfect example of how the plan becomes the reality.
But hang on, if you have thousands of students, how do you find just one without any confusion? That's where the primary key comes in. It's a special attribute that's a unique identifier for every single record. So a student's roll number is a perfect example. Just like your Aadhaar number is totally unique to you, a primary key makes sure that every single row in our table is one of a kind. This is absolutely critical for keeping things organized.
Okay, so we've designed our database with a solid blueprint. Now, how do we actually talk to it? How do we ask it questions and get the information we need? Well, for that we need a special language, and that language is SQL, which stands for Structured Query Language.
Here's a perfect example from the source notes. Let's say we have two different lists of students, student 1 and student 2. With one simple SQL command, union, we can merge them into a single master list. And what's really cool about this is that union automatically gets rid of any duplicate names for us. Super simple, but incredibly powerful.
But SQL's power goes way beyond that. It can handle really complex questions that need multiple steps. Take a look at this. It's a subquery, which is basically a query inside of another query. The inside query runs first, finding all the employees who make more than 4,500. Then, the outside query takes that list and pulls all the details for just those employees. It's like a two-step mission, all done in one clean command.
And SQL isn't just for fetching lists of data. It's also a powerful calculator. Using things called aggregate functions, you can do some really cool analysis. You can get the count of all your products, the sum of your total sales, or the average customer rating. This is where raw data starts to turn into actual, valuable business intelligence.
All right, we've seen how to structure our data and how to talk to it. But now we get to the most important part. What is it that makes a DBMS something we can actually trust? The answer comes down to two powerful guardians that protect our data no matter what. So guardian number one is what we call integrity constraints. The best way to think about these, they're like the bouncers at a club. They have a strict set of rules about what kind of data is allowed to get in, and they make sure no junk gets through to mess up your pristine database.
And this slide from the notes shows us some perfect examples of those rules. A not null constraint basically says, hey, you're not allowed in without a name. It makes that field mandatory. A unique constraint on the roll number says, sorry, we've already got someone with that ID, you can't come in. These are hard and fast rules that act as our first line of defense against bad data.
Now for our second guardian, and this one is the absolute key to reliability, the transaction. A transaction is a way of bundling a bunch of different steps into one single logical unit of work. It's an all-or-nothing deal. And to really get why this is so important, let's go right back to our banking example.
You see, at the heart of every solid transaction is a set of unbreakable promises we call the ACID properties. A is for atomicity. It's all or nothing. C is for consistency. The data always has to make sense. I is for isolation. Multiple transactions can't trip over each other. And D is for durability. Once a change is made, it's permanent, even if the whole system crashes.
And this right here, this is the magic we were talking about at the very beginning. When you transfer money, it's really two things happening: debiting money from account A and crediting it to account B. Atomicity guarantees that either both of those things happen successfully or neither of them does. There is zero middle ground. So if the power goes out after the money leaves your account, but before it gets to your friends, the database automatically rolls back the entire thing. The money is never, ever lost in limbo.
And that really is the whole journey. From the utter chaos of simple file systems to the careful blueprint of the ER model, the powerful language of SQL, and finally, the unbreakable ACID promise of transactions. These are the fundamental ideas that make the digital world you use every single day actually work.
So, we've figured out how to bring control and trust to our data. But what happens when that data gets so ridiculously huge that it can never fit on just one computer? How do companies like Google or Amazon manage information that spans thousands of machines? Well, that is a whole different level of challenge, and it's a story for another time. Thanks for watching.